Welcome back. So now we're going to find the electric field along an axis of a charged ring. So for instance, imagine that the outside edge of this bicycle wheel had a charge on it, some charge density. And we want to find the electric field somewhere along this axis. So this is a really bad rendering of the wheel, kind of at an angle, so we can look at all parts of the wheel and this axis. Okay, so that's where we are starting. So this has a charge density of lambda. And just to label our axes, we have the x, the y, and our z axis here. And we want to find the electric field a distance d away from the center of the ring. So we take a little, same deal as last time, a little charge dq on the ring, and we look at how it affects the point of interest. So this is our electric field. And if we use symmetry here, which is good to use, we have a dq on the other side. And since they're symmetric, that in this case the y components will cancel out. But you can see that as we go around the circle, all the x and y components will cancel out, and we're only left with the z components of our electric field to add up. Let's call this alpha. Alpha. Okay, so same deal as last time. Since we're adding little tiny point charges and adding it around the wheel, we could use Coulomb's law for point charges. So electric field is equal to kq over r squared. And here's our, we'll call it small r. Call the large r our radius. So if we add the electric field, and we only want the z component, so we're going to say cosine alpha. Okay, so we're going to add our E fields, k dq over r squared cosine alpha. All right, so now let's do our substitutions again. We know lambda is equal to charge per length. So lambda times the length is equal to our charge. So lambda dl is equal to dq. Now let's look at this a little further. Our L in this case is an arc length, right? So lambda, or L, for our arc length is equal to r theta. So that's the relationship to go between arc length, radius, and angle. Theta, in this case, must be in radians. Okay, so dl is equal to r d theta. Let's put that all together. Lambda r d theta is equal to dq. Now we can take this to the limit of the whole circle, and d theta will become 2 pi. So 2 pi r is the circumference. So the whole length is 2 pi r, and that makes sense. Okay, so the other thing we need is little r squared. Little r squared. Well, we know that the radius, so if we see this triangle right here, d, the radius, and r. So little r squared is equal to the radius squared plus d squared. That works out nicely. And alpha here is equal to adjacent, or cosine alpha is equal to adjacent over hypotenuse. It's equal to adjacent d over hypotenuse r, which is equal to d over square root radius squared plus distance squared. Okay, putting it all together now. We'll go back to blue. Electric field is equal to integral k. dq is lambda r d theta. R squared is r squared plus d squared. And cosine theta is d divided by r squared plus d squared. Square root. Okay, let's simplify and take out the constants. Well, let's simplify first. K lambda r and d. Theta. And then this is r squared plus d squared to the 3/2. Now this is where it becomes so much nicer than the line integral. R is a constant, the radius of the ring is constant. D, the distance away from the center that we're looking to find the electric field, is also constant. K is constant and lambda is constant. So all of this is constant. K lambda R D. Now we just need to find our limits of integration. Well, if we start at 0 degrees and we go around all the way, how many degrees have we gone through? Or specifically, how many radians? So we go from 0 to, right, 2 pi. Okay, so this is equal to k lambda r d divided by r squared plus d squared square root theta that goes from 0 to 2 pi. So it's 2 pi minus 0, which is just 2 pi. So our final answer for our electric field is equal to k lambda r d divided by r squared plus d squared square root times 2 pi. And there we go. Yay! Okay, well, I hope you've had fun and you get to do it on your own now. Yay!